Alright guys, welcome back to another video. I'm going to pick up on the other questions that we have been working so far from the 2022 Unit 2, Paper 2, CAPE Physics paper. Alright, so just want to make a bit of correction to this question here. Thanks for the person who would have highlighted it. So let's go back to the answer quickly. So the answer for this would be I is equal to 0.5 sine of 314 t. Right, so I think in the previous video the answer for omega, I think I wrote 628 or something like that, so that was incorrect. So the corrected thing is this. All right, but of course it would not affect the other part of the calculations that we're going to do now. All right, so this is what you would have thought if you were to figure the thing out here in terms of omega. Omega is equal to 2 pi f, so 2 pi times 50, that will give you 100 pi, which translates back to be the 314, okay, rads per second. Now the next question asks us to sketch a graph of a one cycle of the waveform in the previous question with the axis labeled, etc., with the period and the amplitude. So in other words, they want you to sketch an AC curve for one period. So I mean, you weren't given any graph, so you just simply need to sketch it. So let's see if we can do that. So they want it for one period, so obviously you need to know what one period looks like in terms of an alternating current. All right, so this would be a close representation of that. It won't be completely accurate, and they want you to interpret the equation that was previously stated here, okay? Given the fact that we're plotting current versus time, we need to understand what the peak value of the current would be. Of course, you'd start at 0, and then the peak value would be the 0.5 amps, okay? So this axis should be labeled as current, and you know that because it's alternating current, the values are going to alternate between the positive and negative values. So at this point here, where it is the negative region, this would be negative 0.5 amps. So that's ideally what they want you to do so far. However, they want you to also take into consideration the period of the wave itself. How you can simply figure that out is by recalling some information. One, the question gave you the frequency, which is 500 hertz. Okay, and then you should be able to remember that frequency and period, they are the inverse of each other. So having said that, you can then transpose the equation to find the period. The period is equal to 1 upon the frequency. So 1 divided by 50, right, will give you the period. In this case, the period pans out to be 0.02 seconds. So having said that, you can now go to the graph and add that bit of information. So right here, where time would be on the x-axis, you would ensure that you put 0.02. So that completes one cycle of the alternating current. And then you could also go ahead and even put what would be half the period, which is 0.01 seconds. Of course, you need to make sure that you have your units on either axis in order to get the 7 marks. Quite a giveaway in terms of the question. So, you know, I don't know what's happening these days with these type of questions, but they're quite simple. All right, if you're able to achieve that, then kudos to you. All right, we want to jump into this next aspect of the question, which speaks to what we call drift voltage, and yeah, pretty much drift voltage. So ideally what happens is that if you have a conductor, let's take for example a cylinder, yeah, the question started off by saying that a cylinder made of n-type semiconductor material of diameter 4 millimeter and length 1 centimeter carries the same rated current as the device in question A. So you would have to go back to question A here and look at the current that is rated, which is 0.5 amps. That's the max current, which you're seeing on the graph as well. So what they want you to do is to determine the maximum drift velocity of the charge carriers in the semiconducting cylinder if the charge density was given as such. Ideally, we're looking at what we call a semiconductor device, yeah. And in most cases, semiconductor device can either be doped, whether negatively in terms of its ability to have free electrons, or it can have mainly positive charges by way of removing the excess electrons and so on. But in this case, it's an n-type material, which means that there's an excess of negative charge carriers in that type of material. However, what they want us to do now is to figure out the drift velocity, and the drift velocity in this case just speaks to the overall or the average speed that each charge or each electrons will have when it moves from one end of the cylinder to the next end. So imagine that you have the electrons here. You want to figure out what would be the average drift velocity as these electrons move itself from one end of the cylinder to another. So that's ideally what they ask you to do, or want you to do in this case. There is a specific formula that we can apply, and this formula is related to, of course, related to electric current, and I'm going to state that equation in a few seconds, but I just want to put a bit of label in here. So of course we know that the length of the thing is 1 centimeter, right? And then the diameter of the system is 4 millimeter. Okay, so we know that information, we know the charge density and so on. So let's see if we can talk about the equation that they want us to, of course, use. We could even go ahead and even write out the different variables from the question. So n is what we call the charge density, right, which just speaks to the amount of charge that is present in that volume of object, really, right? So in this case, we're saying that there's 3 times 10 to the 17 per centimeter cube of charge within the cylinder. All right, so we know that information. We also know the current, which we said is the right in the previous question, which is 0.5 amps. All right. In terms of the length, we know the length and everything. I don't think we might need the length in this part of the question, right? But what we would need to obviously do is to apply the equation for current, especially when you're dealing with the overall movement of each charges in itself. You know that current is the rate of flow of charge, and because it has to do with the rate of flow of charge, we can figure out the speed that these electrons actually travel with. So to do that, we're going to apply this equation that says I is equal to NEVA. I just kind of utilize this acronym, NEVA, something of that nature. You could possibly think of that to remember this equation, and it's just an elementary equation that shows you exactly what happens in terms of the current as it flows through a particular conductor, all right, or a piece of wire in itself. So we can transpose the equation to make V become the subject, because that's what we're focused on, which is the velocity, the drift velocity, right? And the word drift velocity really just speaks to the fact that with these electrons, you're going to collide against the ions in the metal, and because of that collision, you find that they will drift from one point to the next. So that's what we call the drift velocity. Okay, so now that we have transposed the equation, we can quickly talk about each of these variables. So we say that n is the charge density, or the number density of electrons, same thing as the charge density. We can speak about E. E is the charge of an electron, which is pretty much 1.6 times 10 to the negative 19 coulombs. All right, and then of course V is going to be in meters per second, that's the velocity, and then A here speaks to the area of the wire, so that's going to be in meters squared. We're given obviously the diameter, so we can find the area, and we know that because we're looking at a cylinder, right, it has a circular area of that sort, and so the area in this case is going to equal to pi r squared. You can find r from the diameter information, so d divided by 2. So let's see, so we have 4 divided by 4 millimeter obviously divided by 2. That's going to give us simply going to give us practically 0.002 millimeters, or sorry, meters rather, 0.02 meters. So that's R. So once you find R, you can then substitute that into the area equation, R squared, and then that pans out to be 1.26 times 10 to the negative 5 meters squared. All right, having said that, we now have the area. Okay, so let's see if we can apply what we know. So we know the current, which is 0.5. We know N, which is a charge density, which is 3 times 10 to the 17, times that by the area, which is 1.26 times 10 to the negative 5. Multiply that again by the charge of the electron, 1.6 times 10 to the minus 19 coulombs. So once you do all of that, you can work out the denominator by itself and get the answer, and then you divide it by the 0.5. So V in this case should give us a value of 6 times 10 to the negative 7 meters per second. And that completes this aspect of the question. So of course we're going to deal with the next part in another video, but of course you can follow through, comment, and of course if there are any questions that you have pertaining to this, please feel free to ask. Thank you for watching.